Welcome back. So this is Charlie's second talk on dimer models. So yeah, I don't have anything else to say. So please, Charlie.
Thanks, Mitri. Okay, so today, y'all continue from yesterday, and I'll review some of the definitions because, yeah, there was a number of definitions, and if you haven't seen these before, then it goes pretty quick. Okay. Oops. So first, just for some notation, given an integral domain K algebra S, we denote by max S, spec S, and dim S the maximal ideal spectrum or algebraic variety, prime ideal spectrum or affine scheme, and curl dimension of S, respectively. And we denote by with a script Z of I the Zariski closed set of a subset I. Okay, so first we review some definitions from last time. So a dimer quiver on a surface sigma is a quiver whose underlying graph, Q bar, embeds in sigma such that each connected component of the surface minus the graph is simply connected and bounded by an oriented cycle called a unit cycle. So here, this quiver lives on this surface. It's the genus 2 surface. You identify the opposite sides and the vertices around at the corners of the polygon. So these little cycles in the inside, these are the unit cycles, and you just can't have like any holes or anything inside of the unit cycle. And the dimer algebra of Q is the quotient of the path algebra modulo the ideal generated by the difference of paths, P minus Q, where there's an arrow A such that PA and QA are unit cycles. Oh, and my pictures, like what the genus 2 surface are from Wikipedia. If there's something, I don't know how to make that. A perfect matching of a dimer quiver is a set of arrows, which I write with a variable because I'll have polynomial rings in these variables. So a perfect matching is a set of arrows such that each unit cycle contains precisely one arrow in X. And this is the same definition of a perfect matching on a bipartite graph in the surface. So it's just stated in terms of the dual quiver instead of the bipartite graph, but it's identical. A perfect matching X is called simple if the quiver minus the arrows in X, so if you delete the arrows in X, if this contains a cycle that passes through each vertex of Q, and it's called simple because it's the support of a simple module if of dimension vector all ones, if this condition is satisfied. And so we denote by, oh yeah.
Sorry, can I bother you to move your cursor away from the screen?
Oh, yeah. I don't know what you can see.
Yeah.
Is it better?
Or can you make it whole screen or something?
Oh, yeah. Oh, do you see the bottom? Okay.
Yeah. I don't know if it will help, but maybe.
Is this okay?
Yeah, that's great. Thank you.
Okay. Okay, so we denote by script P and script S the set of perfect and simple matchings of Q respectively. Okay, so the dimer quiver we just were considering has that we just saw has 12 simple matchings. And so in these pictures, so the arrows, they're just drawn with edges because it gets too cluttered. And these are the unit cycles, each of these little guys here. The red are the arrows in the perfect matching. So each unit cycle contains precisely one arrow in the perfect matching. And if you draw in the arrows, you find that you can start from any vertex, get to any other vertex and back, even though it doesn't look like it on here because it looks like these are making walls with the red. But because it's on a genus 2 surface, you're identifying opposite sides, you can get from any vertex to any other vertex with the arrows not in red. So the red arrows are the ones in the simple matching. Okay, oops, sorry. So Gore algebra, so again, this is from yesterday. We want to denote by EIJ and by H with the 1 in the IJ slot and zeros elsewhere. And consider the algebra homomorphism eta from the path algebra to the matrix ring over the polynomial ring generated by the perfect matchings. Defined on the vertices I by eta of EI is the matrix EII. So a 1 on the II slot and zeros everywhere else. And on arrows, A by eta of A is just the monomial that's the product of the perfect matchings that contain A times the matrix E, head of A, tail of A. So with a 1 in that slot and zeros everywhere else. So we'll do an explicit example to see this map. And then we extend multiplicatively and k-linearly to the whole path algebra. And the Gore algebra of Q is the quotient of KQ mod the kernel of eta. And I'll use a lambda for the Gore algebra and an A for the dimer algebra. Okay, so the first question is, how do we find the center of a dimer or Gore algebra? So we just kind of do this very simply. We start with the simplest example. This is the dimer quiver is just consists of one vertex and it has 3 loops. And we can draw this on a torus like this. So notice here, so all these 1, 1, 1s, that's just the same vertex 1 here. They're all identified. And the Y arrows are the same. Those are identified and the X arrows are identified. So we just have 3 arrows. And the dimer potential of Q is given by XYZ minus ZYX. And thus I, the dimer algebra ideal, is generated by the relation. So we can take these partial derivatives, the cyclic derivatives with respect to X, Y, and Z. And what we end up with is just that the dimer algebra is a polynomial ring in 3 variables because these dimer relations just give us that each of the variables commute. XY equals, or so the first one says that YZ equals ZY, ZX equals XZ, and XY equals YX. So in this case, actually the algebra is its center and it's the polynomial ring in 3 variables. And later on in the talk, we'll generalize this to higher genus surfaces as well. Oh, and the thing here also to note is there's just 3 perfect matchings. And so actually the center is just generated by these 3 perfect matchings. So I put this in red because we'll see the same thing later. Okay, now consider the dimer quiver Q. This is kind of the second simplest possible example. Just to see the time. So this is called the conical quiver. This was one of the first ones that physicists looked at. And in the math side, this was the first one in a way so that this one was a non-commutative equivalent resolution. So I'll give the definition again later on, but this was kind of the standard example that people looked at. Okay, so this dimer quiver just consists of 2 vertices instead of 1 and 4 arrows. So here you could just draw it, if you make the fundamental domain like this, where my arrow is going, it's just sitting, you can draw it this way or you can draw it with 2 so you can see both unit cycles. There's just 2 unit cycles up to cyclic equivalence. And the 4 arrows, if you just draw the quiver just as a normal quiver, not on a surface, it looks like this. And we call the arrows A, B, C, and D. And the dimer potential of Q, so it's the clockwise unit cycles minus the counterclockwise unit cycles up to cyclic equivalence, is just CBDA minus DBCA. So you just read it off, and it doesn't matter how you cyclically permute these. You could put the, say here, you could put the A in front there, and it doesn't matter, it's the same superpotential. So therefore, I is generated by the 4 relations. So we take these 4 derivatives, the cyclic derivatives with respect to each arrow. So we have 4 relations. And so there are 4 perfect matchings. Like before we saw there were 3 perfect matchings, one for each arrow. Here we have 4. It's because it's so small. So this isn't typical behavior for dimer quivers, but in this case, because the quiver is so small, we just have these 4. And we can write the polynomial ring with the perfect matchings as X, Y, Z, and W, and there's just 1 for each arrow, where each arrow is contained in 1 perfect matching. So that algebra homomorphism eta that I had written before, explicitly in this case, it looks like this. So eta of E1 is just, we have a 1 there, eta of E2, we get a 1 there in the bottom corner. Eta of A is, so we have an X right here variable, but then everything else is 0. Eta of B, here we have a Y. Eta of C, the Z, and eta of D, we have this W here. So they're just, this is kind of concretely or explicitly what the map eta does for this example. So let's let Z be an element of the center of A, and I'll use capital Z for its center. Then for each I, we have that ZEI equals ZEI squared, because it's a vertex idempotent EI. Then because Z is commutative, we can move one of the EIs past the Z. So we get that Z is the sum of cycles. And furthermore, for any 2 vertices, I and J, there's a path P from I to J. So then what we have is that Z EJP, so that's just the same as ZP, because the EJP equals P. And we move the P past the Z, and then we put the EI in there. So what we get is I is generated by differences of paths, or since I is generated by the differences of paths, Z consists of the same number of cycles at each vertex. So we can write it like this. And so this is what the central elements will look like. And for example, Z equal 1, then Z is the sum of the trivial cycles, 1 at each vertex. So this is just, just the standard identity in the path algebra. Okay, So using the relations, we find that the center of A is generated by these four sums. So we have AC plus CA, AD plus DA, BC plus CB, and BD plus DB. So explicitly, this is the generators of the center using those relations from the superpotential, or just the ideal I. Their eta images then look like this. So the eta image eta of AC plus CA is just XE times the identity matrix. The image of AD plus DA is XW times the identity matrix. The eta image of BC plus CB is YZ times the identity matrix, and the eta image of BD plus DB is YW times the identity matrix. So the central elements, this is really from Schur's lemma, they all are just proportional to the identity matrix. So therefore, the center, we can forget the identity matrices because they don't do anything. And so it's just K adjoin XZ, XW, YZ, and YW. And we can rewrite that as the coordinate ring generated by STU and V modulo SV minus TU, where S is equal to XC, T is equal to XW, U is equal to YZ, and V is equal to YW. So Z is the coordinate ring for the quadratic cone, or also called the conifold. So this is how you find the center. Okay, so now I'll just say real quickly about singularities and their resolutions. So a singularity is a point of a variety where the tangent space is too big. So the tangent space is larger than the curl dimension of the local ring at that point. So if you take like this cubic curve here, the tangent space at any point along the curve except where it crosses itself is just 1, right? You just do a tangent line. But here, if you make tangent vectors at this point, it will be 2-dimensional instead of 1-dimensional, because you have a tangent vector going this way and a tangent vector going this way. And so its span is 2-dimensional instead of 1-dimensional, so it's a singular point. A resolution of a singularity, X, is a proper birational map to a non-singular variety Y. Birational just means that X and Y are isomorphic on open dense subsets. Equivalently, their function fields are isomorphic. So if you haven't seen these things before, we'll do a concrete example with a conifold quiver to see kind of how this works. Okay, how do we resolve the center of a dimer or core algebra? So we'll go back to our example. So recall the center is this K adjoin STUV modulo SV minus TU, and we'll call this ring R. The point at the origin, so this maximal ideal, generated by STU and V. So this is a point with coordinates just STU and V. STU and V are all equal to 0. This is a singularity because its tangent space is too big. So you can see this explicitly. This is just the rank of the Jacobian matrix at this ideal. So this is the codimension of the tangent space in A4, 4-dimensional affine space with coordinate ring STU and V. This is 0, so you can just work out the Jacobian and see that the tangent space is too big. Okay, so now we know that we have this singular point, and max R, so this algebraic variety that's singular, admits 2 minimal, and I'll just say they're called crescent resolutions of this point M0. And we'll call these Y plus and Y minus. And we construct these resolutions using the isomorphism that we had earlier. So where S is equal to XZ, T is equal to XW, U is equal to YZ, and V is equal to YW. So since we can, using these definition of variables, we can write T as W over Z times S and U as Y over X times S. And so we can replace T, so this is our birational transformation, with W over Z times S. And so we choose one of these two things to do, or we could replace U with Y over X times S. So everything is fine if we do this, because our ideal, defining ideal for the variety SV minus TU, this is just S times, we can factor out the S and we just have S times the product V minus W over Z times U. And that's also equal to S times the product V minus T times Y over X. So these are really birational transformations. Thus, even when all the S, T, U, and V are equal to 0, so we're at the origin, the ratio Y over Z is free to vary, or the ratio Y over X is free to vary. So therefore, it's called the exceptional locus of the resolution. So this is the pre-image of the singular point M naught. They're both given by a P1 here. So with coordinates ZW in the first resolution and XY in the second resolution. So we have these two P1s, these two minimal resolutions of our singularity. So what we're doing is we're taking the singular point and we're removing it and putting in its place a P1. And so that makes everything smooth and nice. And so this is how it's done. So kind of a concrete hands-on example. Okay, so now magic occurs. Okay. Let D, with that little vector thing, be the dimension vector of a simple representation of our dimer algebra, or Gore algebra, because in this case they're the same, of maximal K dimension. So in this case, D is 1, 1. So there's no simple modules of dimension vector bigger than this. This is the maximal. You can't have 5, 5 or 5, 18 as a dimension vector and have a simple module with that dimension vector. Consider all the indecomposable representation isoclasses of, call them rho, of A of dimension vector T, here being 1, 1, that sit over the singular point M naught of Z. So by sitting over the singular point, I just mean that the annihilator of the module, if you talk in terms of modules, or in terms of representations, the kernel of the representation intersected with the center is just this ideal. So this is what I mean by sitting over the singular point. So because at this point, this maximal ideal M naught, we have S, T, U, and V are all equal to 0, these representations will satisfy, we must have that XC, XW, YZ, and YW are all equal to 0 if we label the arrows as from their variables that are corresponding to each arrow. So there are therefore two families. So there's two families, two ways to get that these four XZ, XW, YZ, and YW are all equal to 0. We can either have the top two arrows be 0 or the bottom two arrows be 0, represented by 0. And because we're requiring the representations be indecomposable, we can't have both Z and W be 0 if we take the left-hand side, or if we take the right-hand side, we can't have both X and Y be 0. So furthermore, we identify isomorphic representation. So this was up to isomorphism. And when you do, you can always when you look at isomorphic representations, you can always rescale so that there's a 1. Here we have on one of the kind of these dashed lines going down are the isomorphism maps. So basically the way this works is these are isomorphic representations if basically the squares commute. So for example, here I go from Z lambda going that way. It has to be the same as if I go down this way, 1 times lambda Z. So I can put a 1 at either place. I'm free to do that because there's this trivial K star action. And then this lambda here is in GL1 of K, so K star, so some non-zero scalar. Okay, and then we can also do this on this side. Just the way this works again is all the squares need to commute when you say these two representations are isomorphic. So like here we go, x lambda equals 1 times lambda x, and y lambda equals 1 times lambda y. So everything is good in the zeros. We have 0 times 1 is equal to lambda times 0. That's all good. So just for each non-zero scalar lambda, we identify ZW with lambda times ZW and XY with lambda times XY, because we're looking at isomorphism classes of representations. So these two families are precisely the exceptional loci from the two minimal resolutions of the conifold. So our pi1 inverse or pre-image of the singular point M0, which was this P1 here, is just this. So we see it right there in the quiver. And our pi inverse for our second resolution was this P1 in blue, and it's the XY arrows. So we have the ZW arrows, these two arrows, and the top two arrows, the XY arrows, as these are the two minimal resolutions we see them right in the quiver. So we find that the minimal resolutions at the center of the Daimer algebra are hidden within its quiver. So the Daimer algebra sees, in this sense, the different minimal resolutions of its center. So this is all, like, I think, completely amazing how this works. And we would like to say that A is, in some suitable sense, a non-commutative resolution of its center. So I'll just give a quick brief history of non-commutative resolutions. So that R be a local Noetherian domain with an algebraically closed residue field K and maximal ideal M. In the mid-1950s, Alexander Buchsbaum and Serre established a homological characterization of regularity. So regularity means we're at a smooth point. I mean, ignoring issues with the ground field. So we're just say over C. R is regular if and only if the global dimension of R is equal to the projected dimension of the residue field over R, and that's equal to the crawl dimension of R. So this is completely amazing. We have this crawl dimension equaling the global dimension, and so we have this homological characterization of if a point is smooth or singular. And in 1984, Brown and Hager-Navis generalized this characterization to the setting of non-commutative Noetherian rings, which are modulo finite over their center. So they took this idea of what Alexander Buchsbaum and Serre had found and placed it in the non-commutative setting. So they said such a ring A with a local center R is said to be homologically homogeneous if for each simple A modulo V, we have that the global dimension of A is equal to the projective dimension of V, and that's equal to the crawl dimension of R. So in the commutative case, I mean, this just kind of directly generalizes the commutative case, because that K here, in this case, is the unique simple module for R, because R is this local ring, so K is a simple module. So here we're changing the simple module K here to a simple module V, but now there could be more than one, so it's taking the place of the residue field. So K, yeah, is just R mod M. Yeah. Okay. So then in 2000, motivated by string theory, we meet David Bernstein and Robert Ley again, that we met yesterday. They introduced the idea of a non-commutative resolution in this context. So according to general relativity, space-time is smooth. However, so this is just a side note. So you can, yeah, just ignore this part if you want. It's in smaller font because this is a side note and it's kind of a the physics background from where this came from. So according to general relativity, space-time is smooth. However, models where the internal extra kind of curled up dimensions have singularities, if the internal space, these extra 6 dimensions have singularities, then they can often more closely model what we observe. So for example, supersymmetry breaking or something like this can be accomplished by having singularities in this compactified space. So there's a problem because on the one hand, we want space-time to be smooth, but on the other hand, we want it to have singularities. So in the internal space, there are objects called d-branes, and living on these d-branes are these matrix-valued functions called chain-pattern factors, and in this case, they're the superpotential algebra. The idea was that these matrix-valued functions could see the singular geometry as smooth, and thereby saving the day. So you have both the smooth and the singular together, and everything was okay because the matrix-valued function saw the singular space as smooth. So this was the idea. Then in 2002, Vandenberg placed the idea of homological homogeneity into the context of derived categories with his definition of a non-commutative Kreppel resolution. And it's much more technical and formal, but it was specifically to have derived equivalences between a non-commutative algebra and the coherent sheaves on different commutative resolutions of the center of that algebra. So the definition goes that a homologically homogeneous ring A, so the definition we had on the previous slide, is a local NCCR, which is short for non-commutative Kreppel resolution, we have this NCCR if R is a normal Gornstein domain, so its center is a normal Gornstein domain, and A is the endomorphism ring of a finitely generated reflexive R module. And I think it's a bit too technical to get into what a Kreppel resolution is here, but the definition is given there. But anyway, I guess the other thing just to say quickly is that the endomorphism part, so the homological homogeneity is replacing the smoothness part. The endomorphism ring part is replacing birationality because in this case, you can't, of course, have the center and the non-commutative algebra to have isomorphic function fields because one is commutative and the other is not commutative. So the closest you could say is at the Morita equivalent, so that and that's what the endomorphism ring condition is giving you, is saying that the function field of the center is Morita equivalent to the tensoring, taking A, tensoring over the center with the fraction field of the center, and saying these two things are Morita equivalent. And that's the substitution for what's replacing birationality. And we'll come back to endomorphism rings a bunch later. Okay, so now back to cancelled dimer algebras on a torus. So recall from yesterday, we had this theorem a lot of people worked on around 2010 about, but in the range of this time. Let A be a cancelled dimer algebra on a torus, and let M be the maximal ideal at the origin of its center. Then the localization, locali A sub M, is a non-commutative equivalent resolution of its three-dimensional normal toric Ornstein center. So we saw this result yesterday, but now this kind of gives where it came from. And the conifold example was the first one people worked out, and that was actually Ishii and Ueda were the first to show mathematically that this is a NCCR, a non-commutative equivalent resolution. In the physics, they had already basically found that they were what they wanted as non-commutative resolution. So that if you would ask them, they say, "Oh, of course, yeah, they're non-commutative resolutions." But for the technical definition of an NCCR, then that was a work from a lot of these people. Okay. Also around this time, Gulada showed the converse. So actually, every three-dimensional affine normal toric Ornstein singularity admits an NCCR given by a cancellative dimer algebra on a torus. So it really shows that the dimer algebras are very closely, the cancellative ones on a torus are very closely related with toric geometry and three-dimensional toric geometry. And so this, I mean, it kind of puts it, since any three-dimensional toric one that could have an NCCR, it has one given by a dimer algebra. So it shows the importance of the dimer of these algebras. Okay, can we generalize the A3 or conifold dimer algebras to higher genus surfaces? So these two, today we've looked at these. The first one was just one vertex and three loops, and the second one was the conifold dimer algebra. Can we generalize these to higher genus surfaces? And the answer is no, not if it's a dimer algebra. So dimer algebras are just for flat surfaces, basically. So the torus or the disk, annulus, things like this. But for higher genus surfaces, you lose everything. Your center becomes just the unit, the central element, which is the sum of the unit cycles. And so but if we use Gore algebras, everything is different. So what we have is, so first, here was the first example for the polynomial dimer algebra. This is the same as the Gore algebra in this case. And we just had this square with this diagonal arrow in it, and it was just a polynomial ring in three variables. But we can also put this on higher genus surfaces. So this was a torus, right? Because we identified the opposite sides. So we do the same thing here. We identify the opposite sides of these polygons. So they're the fundamental polygons of the surface. And it's a genus G surface if it's a, you take a 4, if it's a 4-G-gon, it's a genus G surface, if I'm saying that right. So every other one is going to be the next one in higher genus surface. So I'll re-say this tomorrow when we look more at higher genus surfaces. But what we find is that we actually get all the polynomial rings. So and they all look just like the one that we started with the dimer algebra. the simplest possible dimer algebra. Then we have these ones on higher genus surfaces. So this Gore algebra is on a pinch torus and is a polynomial ring in 4 variables. Then we have the Gore algebra on a genus 2 surface. And this one here is a polynomial ring in 5 variables, and so on. So we just go each polygon with, so it's all, these are all, I should say the polygons are all even number of sides, because we're identifying opposite sides. And these give us all of the polynomial rings, not just the 3 variable one, but all of them. Okay, what about the conifold? Can we generalize that also with the Gore algebras? We certainly cannot with the dimer algebras. So the answer is yes. And so we get these as well. I don't know if you can see so the shaded region is the, hopefully it's visible. The shaded region is the fundamental polygon. And these, so that here there's like 2 arrows going this way, 2 arrows this way. And I should say this is joint work with Karen Bauer. So finding these algebras with the Gore algebras. And yeah, so here was the one right here was our conifold that we just spent all the time looking at, and now we go to higher ones here and so on. So so a first question to ask is, what are the properties of these? Are they Noetherian, not Noetherian? Are they going to be like the cancelative dimer algebras on a torus? So these actually are all Noetherian Gore algebras. But these are the only Noetherian examples on higher genus surfaces. So besides the torus case, so the flat case, for all the higher genus ones, these are the only known examples of Noetherian Gore algebras. So the question then, because we're interested in the geometry, is we need to make some sense of the geometry of a non-Noetherian ring. And because anything besides these kind of simplest examples, everything will be non-Noetherian. I mean, this isn't a proof, but as far as we've been able to tell, we haven't found anything else that's Noetherian.
Okay,
So,
Charlie, maybe we can stop in 1 or 2 minutes. Is that?
Yes, yeah.
Okay. Yeah.
So I'll start this part briefly, and then I'll continue tomorrow.
Yeah, sounds good.
So the question is, what is the geometry of a non-Noetherian? Oh, so the motivation for this is all of the so remember from yesterday, the centers of the the centers of the non-cancelative dimer algebras were non-Noetherian, and the Gore algebras also corresponding with these were also non-Noetherian, had non-Noetherian centers. So if we want to explore the geometry or the central geometry, or how the center relates to the representation theory of non-cancelative dimer algebras on a torus, or non-Noetherian Gore algebras in general, we need to have some notion of geometry in a non-Noetherian setting. And so the next part will be about this, and I'll just kind of set up the motivation. Is just the question is, what is the geometry of a non-Noetherian integral domain K algebra? So if we want to kind of have a version of a non-Noetherian coordinate ring. And so of course the first answer you could say is it's just a scheme, right? But schemes are still abstract, and there's nothing you can visualize with, if you say it's a non-Noetherian scheme. There's no associated concrete geometric picture that you can put with that. And so that's where I'll start tomorrow is I'll talk about non-Euclidean geometry and then use it to make sense of the non-Euclidean dimer algebras and Bohr algebras. Okay.
Great, thank you. Thank you for the talk. Any questions? Okay, so no questions today. So let's thank Charlie again, and